Hey everyone, welcome to this explainer. Before we jump in, maybe just take a quick breath, settle in. Let's step away from all the noise of our day for a bit and look at the invisible chemistry that is, literally, quietly powering our modern world. Today, we're going to explore the elegant, silent pulse of the lithium-ion battery.
Seriously, just take a second and look at the device you're using right now, whether it's your smartphone, a tablet, or your laptop. Have you ever stopped to wonder what's actually keeping it alive? There's this quiet, tireless energy source tucked away inside. It doesn't make a sound, it has zero moving mechanical parts, yet it is continuously working to keep you connected to the world.
So the hero of our story today is the lithium-ion battery. And honestly, without any hype, it is simply one of the most elegant chemical inventions of the modern era. It's what we call a secondary battery, which is just a fancy way of saying it's rechargeable. It was designed to be super lightweight, incredibly efficient, and it just seamlessly blend into the background of our lives, powering our conveniences without us ever needing to give it a second thought. In fact, this quiet invention was so revolutionary that it won the Nobel Prize in Chemistry in 2019, basically because it created the wireless world we live in today.
Okay, part 1. Inside the lithium-ion cell, visualizing the architecture.
So let's actually look at how this thing is built. Instead of thinking of a battery as some complicated, intimidating machine, just picture it like a cozy, layered house. On one side, you've got the positive side, the cathode. Over on the far side, there's the negative side, the anode. And right in the middle, that's the quiet, protective middle ground separating the two. It's a beautifully organized system where every single layer has a very specific, peaceful job.
Let's gently break down these house components. The positive electrode, the cathode, is made up of layers of lithium cobalt oxide. Then, the negative electrode, the anode, is made of porous carbon, usually graphite. Actually, just think of that graphite like a microscopic sponge. Sitting right between them is the electrolyte, which is the soft polymer gel acting as a transit pathway. And finally, we have the separator. It's a semi-permeable plastic wall that stops the two sides from touching, so no short circuits, but it's perforated just enough to let our tiny lithium ions pass through safely.
The really crucial takeaway here is that this specific architecture creates what chemists call a secondary battery. Unlike those older primary batteries that you use once and then throw away because their chemical materials are permanently consumed, the lithium-ion cell is all about renewal. Its chemical reaction can be safely and repeatedly reversed for countless cycles.
Moving on to our next section, the gentle dance of ions, the daily commute.
Let's see how this actually works in practice. Picture the chemistry as this calm, orderly migration. A battery basically lives in two states, right? Charging and discharging. Now think of charging as a non-spontaneous process. It's kind of like gently pushing a boulder up a hill. It requires an external push, in this case the voltage from your wall charger, to store energy. Discharging, on the other hand, is completely spontaneous. That's the boulder freely and steadily rolling back down the hill, naturally releasing its stored energy to do the work of lighting up your screen.
You know what's really fascinating about this whole process? It's what is missing. There is zero metallic, solid lithium in here. Pure lithium is highly reactive in water and can actually be quite dangerous. Instead, the real genius of this cell is that it uses lithium ions. It's simply the safe, peaceful transport of these charged particles back and forth across that gel medium.
So, let's map out this charging commute. When you plug your device in, the external charger applies a voltage. This push gently evicts the lithium ions from their comfortable home in the positive lithium cobalt oxide. They travel right across the gel, slip through the separator, and settle into that porous graphite sponge on the negative side. In chemistry terms, the equation is pretty elegant. LiCO2 plus carbon becomes Li1-X CO2 plus ClIX. Basically, the ions have just relocated.
And then we have the discharging return. When you unplug and start using your phone, a spontaneous migration kicks off. The lithium ions naturally want to go back home to the positive side. As they flow smoothly back through the gel, they leave their electrons behind. And because electrons cannot travel through that separator, they're forced to take the long way around through your device's external circuit. That flow of electrons, that is the electrical current powering your screen, your apps, and your audio. The ions return home, completely resetting the equation back to LiCO2 plus carbon.
Next up, powering modern life, the silent heartbeat of our world. Let's zoom out for a second and ask, why does this tiny microscopic commute even matter? Well, for starters, it powers our everyday companions. This battery produces roughly 3 times the voltage of those older nickel-cadmium batteries. And because it uses lithium, which is literally one of the lightest metals on the periodic table, your laptop doesn't weigh 30 pounds. I mean, if it used an old car battery, you need a forklift for your backpack. It is incredibly compact. Oh, and wonderfully, it has absolutely no memory effect. meaning it doesn't artificially forget its true charge capacity if you happen to plug it in before it's fully dead.
But the coolest part is how beautifully it scales up. This exact same gentle dance of ions is what powers modern electric vehicles. By stacking these cells, EVs can store massive amounts of energy for long-range travel. They even use regenerative braking. That's where the car captures its own kinetic energy when you hit the brakes, forcing the ions back into the graphite to recharge on the go. Plus, with vehicle-to-grid technology, these parked cars can actually pulse energy back into city power grids to help stabilize them during peak hours. It's just a remarkably versatile system.
Finally, a peaceful takeaway: the endless cycle.
As we bring this explainer to a close, let's just lower the energy for a moment. If you're a college student feeling stressed or totally overwhelmed by the complexities of your coursework right now, I want you to take a breath and just look at the simplicity here. In a lithium-ion cell, there is no chaos. Energy is never truly lost, it is simply transferred. It's a reliable, perfectly balanced exchange. Just a quiet, endless cycle of renewal where things move away and then they naturally find their way back home to provide power. It's a really comforting reminder that, at the microscopic level, the universe operates on beautiful, predictable balances.
So, the next time you pick up your phone or crack open your laptop, maybe give a little nod to the millions of lithium ions dutifully making their daily commute just to keep you connected. It kind of makes you wonder, what other invisible, elegant energy dances are happening in the physical world around you right now? Keep that gentle curiosity alive. Thanks for tuning into this explainer and keep exploring.